Dear Leung Pok Yin, it is the day of your defense of your PhD project. I'm very happy to chair it. I have to say it's the first time I chair it, so I'm nervous as you, maybe not as much as you. So I'm very curious to hear about your presentation. I would like to welcome very warmly Agathe Koller from Ostschweizer Fachhochschule, who is co-chair of this PhD, and also Matthias Kohler and Fabio Gramazio, who are PhD supervisors also. We will have about 60 to 70 minutes for the presentation and questions from the examiners, and then also time for a few questions from the guests, and then afterwards we will have to go to closed rooms to discuss and make our decision. And afterwards, I hope there's time to celebrate. So the floor is yours. Good luck.
Thank you. Good afternoon, professors, colleagues, friends, and families. My name is Victor Leung from Gramazio Kohler Research. Today, I'm excited to present to you my PhD work that I have conducted under the supervision of Professor Matthias Kohler, Professor Fabio Gramazio, and Professor Agathe Koller. Before I introduce my topic, allow me to introduce a little bit of my personal background. So I grew up in Hong Kong, and if you know anything about Hong Kong, well, there's no space. And so as a kid, I stayed at home a lot. And thanks to my father's influence, I picked up a lot of indoor hobbies like electronics and woodworking. And being a 90s kid, I also picked up computer programming for fun. When I entered architecture school, digital fabrication were just starting the revolution. But I immediately clicked with the idea of programming machines to make things. So for the 2 years after my bachelor, I joined a startup company that was trying to build bespoke timber pavilions. It was a three-man show, so I had to do everything from designing timber joints to programming CNC machines. But what I was really proud of, at least from a technical point of view, is the automated workflow from design modeling to the generation of G-code. However, later on, as I joined MIT for my master's degree, I realized that everybody doing digital fabrication is doing the same thing. So I decided to look at what is the next step after machining. And that, for me, is assembly. So my thesis back then, which provided the groundwork for what I'm presenting today, was about how designers can spend a little bit of extra effort during modeling to annotate the assembly motion and sequence of things. And that information can be used to generate interactive instruction for showing how things are put together. The topic that I'm presenting today may look larger and more complex than putting toys together. But it is the same motivation and the same curiosity of extending digital fabrication beyond fabrication to the assembly process that follows it. The title of my PhD thesis is Distributed Robotic Tools for Spatial Timber Assembly with Integral Timber Joints. Distributed robotic tools is a term that I invented to describe the robotic end effectors that are detached from the robot, which is the focus of this study. Spatial timber assembly refers to the assembly that happens in 3D space, as opposed to planar assembly that are 2.5D. Integral timber joints often refers to tight-fitting carpentry joints. However, its defining characteristic is really about the structure load that is transferred from wood-to-wood connections. The larger picture that motivates this research is that automated timber assembly is becoming more and more relevant. Timber as a construction material is re-emerging as a potentially more sustainable alternative than steel or reinforced concrete. Robotic assembly can also be a viable alternative to address the lack of skilled labor in the construction sector. Moreover, our institute is one of the very few places on Earth that has a large-scale robotic facility, the RFL downstairs, that is capable of developing and prototyping robotic processes at an architectural scale. Now, let me start with a short summary of the current state of automation in the field of timber construction, looking at it from the perspective of how information and material are combined during construction. The first step in the timber construction process is raw wood processing, which is already a highly automated process with a mass production paradigm. The second step is the beginning of a data-driven and design-driven process. The workflow includes architectural design, joint design, and structural engineering. In order to support this information-intensive workflow, specialized CAD software have already been developed by the industry. For the fabrication of timber parts, automatic joinery machines have been developed for more than 30 years, and there are a handful of manufacturers that makes them. In general, planed timber elements enter the machine from one side, get machined, and exit from the other side. Inside the machine, there are different machining tools for making all the joints needed for an entire timber project. However, what is special about this machining process is not just the machine, but rather how the machining programs are generated automatically. You see, in timber construction, there are many geometrically unique components, and if they are processed using a traditional CNC workflow, a programmer would need to click through every one of them. Fortunately, in the timber machining industry, this step is mostly automated, allowing the CAM software to automatically parse each and every unique components and to generate their machining programs automatically. This workflow is quite unique, and it means that not only the joinery machines are automated, but the generation of data that would go into these machines are also automated. The automation of these two parts, the digital and the fabrication, are the fundamental components for digital fabrication. In contrast to the machining process, the automation for assembly, which is the core topic of this thesis, is less developed. In the industry, the advancement was mainly focused on the assembly of planar prefabricated parts. For example, machines have been developed for light timber frame construction. These automatic systems combine timber machining and various assembly stations for making prefabricated walls and floors. Similarly, the assembly of floor trusses and roof trusses. You may notice that all of these machines look like an assembly line. In fact, these machines are often optimized for a specific geometry and therefore are not so flexible for accommodating customs designs. In addition, the CAD and the CAM software for designing these assemblies and controlling these machines are proprietary systems. This limitation, combined with an inflexible machine setup, limited their application to utilitarian designs. In many cases, these timber components are designed to be hidden away from the architecture, and therefore, we are not very interested in these things. Perhaps a counterexample of a very complex yet attractive design is the sequential roof that is right above us. Despite its fluid appearance, it is still a planar assembly. Notice that the automated gantry robot for assembling it is not even as complex as the robotic lines, production lines we saw. The main difference, I think, is the automation of the digital workflow. In this case, it is not just the cutting instruction that is automated, but also the assembly instructions for the robot. While this project have demonstrated a high level of automation for bespoke planar assembly, my thesis investigates whether similar automation can be applied to robotic arms doing spatial assembly. So what is special about spatial timber assembly? There are many things, but one thing for sure is that we don't find many examples in the industry, and the state of the art is mostly in research projects. For example, the MES DFAB Robotic Pavilion that some of you actually participated in, and the DFAB House Spatial Timber Assembly. The challenges involved in spatial timber assembly can be roughly characterized into 4 types. I will explain what they are using the DFAB House project as an example. Being one of the earliest spatial timber assembly projects, the researchers have found that the accuracy of a large-scale robotic platform is much lower than what is needed for timber assembly. And this is the first challenge, positioning accuracy. Fortunately, our lab is equipped with an indoor optical tracking system called the iGPS, which can monitor the position of the robotic gripper accurately and therefore make closed-loop corrections. However, when dealing with long timber elements, the accuracy at the 2 ends of the beam are much worse than the middle. The researchers found that it was not possible to assemble simple joints like this one. This is the second challenge, joint alignment. In this project, the researchers decided not to use integral timber joints at all, and they have circumvented the problem by using butt joints, accepting the misalignment, and fixing the incorrect geometry later. The third challenge is stability during assembly. This is the major difference between a planar assembly that can be easily supported on a planar platform and spatial assembly, which because of gravity tends to fall down. Here, the researcher addressed this problem by first assembling the corners of their modular timber boxes, which formed a stable tripod to support the rest of the structure. Finally, the fourth challenge, which is also the problem that is least addressed, is how to make connections automatically. In the DFAB House project, this is not addressed at all. The robotic process has to be stopped, a worker has to set up a ladder, install the fasteners, and this back and forth repeats for every timber element. Among the 4 problems, only the positioning accuracy problem is more or less resolved. The other 3 problems can be seen in other spatially assembled timber structures, in one way or another. These challenges limited the choice of timber joints for robotic assembly, and in many cases, to structurally less efficient ones. In some of these examples, the robotic process even required more manual operations than robotic operations. The only relevant robotically assembled timber joint project is a research called Robotic Integral Attachment. The researchers found that using a robotic arm to push tenon joints into the mortar side is not a good way to tighten them. Although they did not explain in details why, but I do suspect that the pushing force from the robot is not enough, and the fact that they are pushing only from one side. While these previous projects may have addressed 1 or 2 of the challenges that I mentioned, a combined solution have not been attempted before, and therefore I decided to use an exploratory research method to conduct this thesis. This method may be unfamiliar to some of you, so here is a short introduction to what you're about to see. I started the exploration by developing an assembly method that is considered a working hypothesis. While this hypothesis did not solve all the problems at once, it is through many observations and small iterations that the hypothesis was refined and improved. And it is during this iterative process that knowledge is generated by making new discoveries and understanding new relationships. In the rest of this presentation, I want to give you an idea of what these developments and observations look like. However, because there are many topics and limited time, I will only be able to say 1 or 2 sentences for each of these topics. If you're interested in some of them, I'm happy to get into the details after the presentation. If you find it hard to follow, I promise it will make sense at the end. So, let's begin. The entire thesis can be divided into 5 exploration phases. The first phase started with a prototyping of a clamping tool. The second phase went on to test the clamps with the robots. The third phase focused on complete automation of both the digital and the robotics workflow. The fourth phase tested a screwdriver concept. And the fifth phase focused on integration with other disciplines. These descriptions are extremely simplified. In reality, each phase contained many developments and experiments. For example, the development of assembly strategies, such as how to apply assembly force and deal with inaccuracy. Mechatronics development, including hardware, electronics, and control software. Finally, similar to my master thesis, studying how timber structures can be designed such that the robotic assembly instructions can be automatically generated. 3 large-scale demonstrators were designed and constructed during round 2, 4, and 5. And after each phase, a thorough analysis was performed to understand what is working, what is not working, because understanding why is the most important goal in this thesis. In the first exploration phase, the focus was to start by addressing the problem of making connections. By observing manual assembly processes and the tools that they use, I had the idea of deploying multiple assembly actuators, 1 at each mating joint. By using multiple actuators, it is flexible to position them wherever the joints are located. However, it would be difficult if each of the actuator requires a robot to hold it. Not only because robots need space to maneuver, but because it is not scalable. Therefore, I hypothesized a scenario in which the actuators are attached to and hanging from the partially assembled structure. The attachment of the tools can therefore be performed even with 1 robotic arm. After all the actuators are in place, the same robotic arm can bring the next piece of timber towards the joint for the assembly. Because these actuators are no longer tethered to the rest of the robotic system, I call this a distributed robotic tool approach, and therefore the acronym DIRT. One of the challenges of using distributed device is to control them to make them move synchronously. In addition, the robot needs to attach the tools to the structure and to retrieve them afterwards. The first prototype is a robotic clamping tool, and that is designed to assemble lap joints that are 90 degrees. I started by measuring the clamping force required for tight-fitting lap joints. This gave me an estimation for the selection of linear actuator and motor driver used for the clamping action. Then I designed a hanging mechanism that would allow the clamp to hang onto the wood. This proof of concept device allowed me to test two of the most important operating principles in the dirt concept. The first is the ability for an end effector to operate while hanging from the timber beams. Apart from the orientation you see here, other orientations have also been tested, and the hanging works pretty well. The second is the application of assembly force locally at the joint. The clamping mechanism operated smoothly without any wedging or jamming effect during the joint closure. This is interesting because lap joints containing parallel faces behaves like an old wooden drawer. You need to close them carefully while ensuring it's parallel to avoid jamming. However, what was found here is that jamming is not a concern, and that also means that many traditional lap joint designs can be clamped robotically. Regarding the mechanical hardware, one of the actuator broke after I repeated the experiments a few more times. However, this was actually good because it gave me a better idea of how to design the hardware in the next iteration. Specifically, the design philosophy is now that the motor should enter protection instead of mechanically destroying itself. Regarding the assembly strategy, the demonstration also revealed a serious problem with my initial hypothesis. The idea that the robot can let go of the timber and give it to the clamp is not very generalizable, and that can only work in this perfectly balanced posture. Therefore, in subsequent exploration, I decided to have the robot hold on to the beam and support its weight during clamping. This way, the clamp do not have to support the beam, and the beam is free to be in any orientations. In the second exploration phase, it was much more ambitious. The goal was to integrate the clamps with the robotic arm in RFL and to test their operation by assembling a large-scale demonstrator. Another ambition is to redesign the clamp to accommodate angled lap joints. The new clamp design used only one clamp jaw instead of two and relocated the hanging gripper mechanism to the side of the beam. This way, the clamp can accommodate lap joint angles that ranged from 25 degrees to 90 degrees, and a mirror version of the clamp was designed to accommodate the angles from 90 to 155. On the electronics side, an embedded controller was implemented to control the motor and to allow wireless communication. The motion control algorithm is the key to allow synchronization between the clamp and the robots. The principle is based on a mutually agreed motion profile that would start and end at the same time. The wireless network was also a custom implementation, optimizing for low latency and high reliability even when there are occlusions. The synchronization control is based on a concept called distributed control system. It allows individual robot controllers such as the clamps and the ABB robot controllers to report to a top-level controller that is responsible for their synchronization. Finally, the large-scale demonstrator was designed by an MAS student, Frederick Brison, also in collaboration with Dr. Davide Tanadini from the chair of structural design. He is a long-term collaborator under the same NCCR research umbrella. While the demonstrator was intended to look good, it is also intentionally designed for studying different clamping orientations, and with up to 3 simultaneously moving clamps. Apart from those, there are some foundational pieces that have to be fixed manually to the ground. Being the first large-scale demonstrator, the focus was to validate the most difficult part, which is the synchronous clamping movement. What you're seeing here is the robot using a parallel gripper to support the weight of the beam during the clamping operation. While the synchronous motion worked very well, the main challenge was the poor alignment between the two sides of the joint. Here, different from the precedence project, the iGPS tracker was not used because of the amount of timber elements that would block the sensor from seeing their reference stations. Therefore, my plan to address misalignment was to introduce chamfering on the joint edges. When the joints are being forced together by the clamps, the chamfering can provide a ramp that would guide the two halves into alignment. During the demonstration, I have found that 5 to 8 mm of chamfering works most of the time. However, in some cases, the misalignment was too big. There was no option but to manually push the structure until they align. In order to understand the misalignment problem better, I systematically analyzed the deviation error on the robot side and on the stationary side. On the robot side, I found that the mechanical connection between the robotic arm and the bottom of the gantry was not calibrated. I also found that the Z-axis of the gantry is not stiff enough. This caused the entire robotic arm to swing from side to side by a small amount when the axis is fully extended. Finally, I found that the position error at the end of a long timber beam to be more significant than what I had hoped for. On the stationary side, I found that the partially assembled structure can deform quite significantly, especially for the poorly supported beams. After all, the structure is by definition incomplete during assembly. This discovery inspired a new deformation-aware design principle in the fourth and fifth exploration, which we will explain soon. In addition, I also found that lap joints in general suffer from low initial rotational stiffness, which is kind of a fancy way to say that there is a gap. Finally, the joints are simply held by friction, and they have a tendency to open up during the subsequent movement when there are small vibrations. This discovery motivated the development of a screwdriver tool that I will show in the fourth exploration. The second major test on this prototype is the beam transfer action. It is the robotic movement that brings a timber element through the obstacles into the partially assembled structure. Unfortunately, even using the latest motion planning algorithms at the time, they often cannot find a solution even after searching for a long time. In some cases where the algorithm returns, the solution can still be incorrect and contain collisions. Fortunately, I got help from a motion planning specialist, Dr. Yizhang Huang, previously from MIT, now in ETH. Not only he was able to identify the cause of the collision problem, he also developed a custom collision checking algorithm specialized for timber assembly. We also added a short segment of linear motion to slide the timber into the clamp jaw, which turns out to significantly increase the planning success rate. Here you can see the linear sliding movement before the clamping movement. The goal in the third exploration is to test the rest of the robotic process that was not yet tested. The highlights being the robotic attachment and detachment of the clamps on the structure. No new demonstrator was designed for this phase because the bus stop demonstrator can be used again for the new tests. The major challenge in this exploration is to plan the sequence of tasks that the robots needs to perform. In collaboration with Yizhang, we came up with an easy-to-use method for planning assembly instruction. And the idea is to describe a robotic process as a series of actions in a flowchart. Loops and conditionals can be used to control the sequence of events. And every time the flowchart encounters a white box, an action is performed. This white box is actually called an action group. Within it, the designer can specify the actions of the robots, the tools, and can even include manual operations. Different action groups can have different combinations of these actions, and once they are specified, they can be used in the flowchart in any order, and can even be reused in a different project. Once the motion tasks are determined, the robot's Cartesian targets were computed automatically. These geometrical data were extracted from the design model of the timber structure. Once the tasks are planned, it needs to be filled with trajectories. Here, the new challenge is that all the motions are chained together, so planning one trajectory affects the others. Moreover, there are some trajectories in the list that are more difficult to plan, and those have to be planned first. In order to address this, we came up with a method to plan non-sequentially, while ensuring the trajectory space continuum. Here you can see the results of the more optimized motion planning. The long beam successfully navigated around the obstacles before sliding into the narrow passage of the clamp jaw. Here is another test of holding the timber using an unbalanced posture, and that was found to be okay as well. Here you see the robot picking up a clamp automatically from the storage station and then bringing it to the structure. You can see the pre-drilled holes on the column for the hanging mechanism to grapple on. During attachment, the misalignment problem was worse than what I have expected, and there are many times that I had to jog the robot with a joystick until the hanging mechanism clicked into place. Here in a different view, you can see me jogging it upwards until the pins align. When retrieving the clamps, alignment was even more difficult because the allowable deviation of the tool changer is only 1.5 mm. So I added a wireless camera on the robot side to look at the tool changer during alignment. This allowed me to make adjustment by looking at the computer screen. That piece of paper with a printed scale on it turns out to be much more effective than trying to eyeball the amount of deviation while jogging. Finally, on the hardware side, I want to fix the collision problems I had with the cables in the previous rounds. This is actually a very unique problem for spatial assembly because the robotic arm needs to move in all the different degrees of freedom. And because the movements are non-repetitive, it is difficult to predict the movement of the soft cables and to avoid collisions. Here, I found that the addition of a cable retract system and a wrist cable guide can fix the problem in a reliable way. In the fourth exploration, the goal is to test two interesting concepts that are high risk but potentially high return. The new concept is an assembly tool based on a screwdriver mechanism. It can expand the range of assemblable joints to include lap joints that are non-planar. The second concept is to address the deformation that occurs in the partially assembled structure. If successful, it could greatly reduce the chance of misalignment during assembly and therefore reduce the need of human intervention. The first important development is the screwdriver tool. It was developed in collaboration with Mr. Marco Rossi, a mechatronic engineer from OST Rapperswil. The operating principle of the screwdriver tool uses a long screw to pull the two sides of the joint together. The main difference from the clamping mechanism is that the assembly force is in the middle of the joint, not on the outside. The central pulling screw allows the screwdriver to assemble non-planar lap joints. And at the same time, the rotating mechanism also allows the installation of a fastener, which can prevent the joints from opening up during the subsequent assembly. Different from the robotic clamps, the screwdrivers are attached to the robot side instead of the stationary side. Here you can see one of the screwdriver is held by the robot directly, while the other one is hanging on the moving beam. It is also possible to use a conventional parallel gripper for holding the wood. In any case, the rest of the screwdrivers are retrieved automatically by the robot, but there's only one. Here, you can see an upgraded version of the camera docking system. It uses a calibrated computer vision marker that allows the robot to autonomously align with the docking adapter. The second important development is deformation-aware design principle. The concept consists of two parts. The first is the evaluation of the partially assembled structure to predict instability and to determine if the deformation will affect the subsequent alignment. The second part is a series of techniques for correcting the deformation. In this example, a diagonal element is designed to be assembled after the column, such that the straightness of the column can be ensured. This correction mechanism relies on the edge chamfering on the joint, and by forcing the joint together, the chamfering acts as a guide to guide the structure back to correctness. In this example, the addition of this column is potentially unstable, but it does not affect the assembly for the next joint because the joints are very close together anyways. While this column is still unstable on the other plane, the next diagonal element creates a triangle that would stabilize it. And for this demonstrator, this is all it needs to create a stable base for assembling the rest of the roof structure. Speaking of which, this demonstrator is named the Hyper Hut because the base resembles a timber hut in the Alpine mountains and the roof is a hyperbolic parabola. While the Hyper Roof is mainly designed to showcase the ability to assemble non-planar joints, the fact that it is a double curved surface also demonstrated a high structural rigidity that is achieved through form. Therefore, the roof is supported only by 5 columns instead of 6. The structure also used 3 different types of timber section sizes that corresponds to the structural needs. And although the joints have different dimensions, the screwdriver can assemble them all. Finally, the demonstrator also tested many traditional joint details, such as dovetailed lap joints that can better resist tension, and housed lap joints that have much higher rotational stiffness. By the end of the 4th exploration, the robotic assembly process have already achieved a high level of autonomy. And me, as the operator, is simply monitoring the system and loading material from time to time. Therefore, in the fifth exploration, the goal is to scale up the system by combining both robotic clamps and robotic screwdrivers. This demonstrator in this exploration is designed by a team led by my structural collaborator, Dr. Davide Tanadini. They came up with a reciprocal spatial structure, a box that would require only 4 screws to achieve interlocking. The whole pavilion consists of 3 of these boxes, and since one of them is cantilevering, this demonstrator is called the canti box. The main challenge that came from a reciprocal structure is that stability can be very bad before it is completed. However, I found that the deformation awareness principle can still be applied. Instead of using permanent diagonal bracing, temporary scaffolding can be used to prevent deformation before it happens. The joints used in this demonstrator is also designed by Davide, using a method developed in his PhD thesis. It is able to customize the geometry of each joint based on local load conditions. From the robotic process perspective, this test demonstrated the flexibility of the clamping and screwing assembly method to accommodate different joint details. On the hardware side, the camera marker alignment method is extended for the attachment of clamps. This eliminated all the manual jogging needed during the clamp attachment. My collaborator Yi Zhang also tested an implementation of the latest AI planning method called PDDL Stream. This optimization allowed direct transfer of the robotic clamps from one location to another, and thereby eliminating redundant movements between the storage location. After 5 development rounds and 3 demonstrators, I found myself in a period of reflection, and there were certain tasks in the process that had persistently refused to operate reliably. For example, the joint-to-joint alignment of clamp joints and the alignment of screwdriver tips with the pre-drilled holes. There was a spark of inspiration as I looked at the execution logs, and the idea is to think about success and failure as a probability. After all, no industrial process is 100% reliable, and it is only a question of how often it fails and how much failure is acceptable. There are 2 main factors affecting successful alignment. The first is deviation, and the second is whether there are correction mechanisms used. This concept was developed further into a new hypothesis. I call this the probabilistic method of spatial alignment. The model contains a simple equation that relates the probability of successful alignment to a number of factors. The first is deviation, which is a random variable that can be measured and predictable with statistical methods. The second is allowable tolerance. And finally, if correction method is used, its range and probability of success. This concept can be applied to passive correction and active correction methods like these. This model is extremely useful because it can answer the questions that we always have when designing a robotic process. For example, is the robot accuracy enough? Do we need a correction mechanism? Do we need scaffolding? Or how much chamfer should I add to the joint? This model can provide a statistical prediction for each alignment action and, by extension, for all the planned action in the robotic process. While this model is still a hypothesis, it has the potential to be generalizable and applicable for every robotic assembly processes in the future. As we approach the end of the presentation, I would like to conclude by looking back at the 4 grand challenges I laid out in the beginning. The robotic clamps and screwdrivers that I proposed have demonstrated a fully automatic way of making connections. The application of assembly force locally at the joints enabled the use of edge chamfering as a way to align tight-fitting joints. This error correction effect was found to be exploitable to provide global error correction to the entire spatial structure. This effectively turned the disadvantage of using tight-fitting joints into an advantage that can be used to ensure accuracy. By analyzing the risk of deformation, scaffolding can be planned during design to ensure stability during assembly. While there are still misalignments that are too big to correct, the newly hypothesized probabilistic model of spatial assembly should provide a quantifiable method for addressing this issue in the future. At the beginning of this presentation, I asked the question whether spatial timber assembly will ever be as automatic as what we are expecting in digital fabrication. I tried to find this out by taking on a journey to develop the technology, and in the journey, I discovered new problems, explored their limitations, and identified new relationships. I hope that by now, we all have a better understanding of what it means to assemble spatial timber structures. Looking beyond the topic of timber assembly, the distributed robotic tool concept offers a new way of using industrial robotic arms for construction automation. This method effectively separates the generic problem of spatial manipulation from any process requirements, and you can scale up to use any number of tools without needing a lot of robots. It can be extended to other assembly processes, jointing methods, and even other material systems. The ability to combine different tools in one unified system and the ability to easily swap between them offers a new way to think about digital fabrication in a much larger picture. We are no longer limiting to make a one-trick per research project type of research, but seeing it as a set of robotic skills that can be built up and combined to assemble even more complex objects. Before I finish, I would like to thank everyone that kept the boat afloat during this journey. Thank you to my professors who have steered the research in the right direction. Thank you for my collaborators who have lent me their superpowers. Thank you to my colleagues who have listened to my troubles and offered me clarity. Thank you to my friends and family members for all the love you have given me. And finally, thank you for you all for attending this presentation. I hope this is worth your time. Thank you very much.
Thank you, Victor, for the very dense and very professional presentation. And we now have some time, about half an hour or something like that, for questions from the examination board. So maybe our guest would like to start.
Yeah, thank you, Victor, for this impressive work. Very, very impressive. I have a question about these two different tools you've developed for making connection. What would be your advice to continue on this direction, for example, screwdrivers, or you will say that the approach with clamping system would be the better way to go?
I approached this problem by studying what connection details I would like to assemble, and I have picked lap joints as my starting point. And I looked at how lap joints should be best assembled, and then I designed the tools according to the jointing system. So I think depending on what type of structure you would like to assemble, then it would be the result of that, I think. So for the lap joints that I looked at, both worked very well. The screwdriver method do introduce a new screw hole in the middle of the joint, so that might not be ideal for certain structural application or rainwater ingression. The clamps is how carpenters will also assemble structures as well. However, it does have its limitation on non-planar stuff because you then have non-planar surfaces that is very hard to clamp together. So I think it's really a question of how or what you want to assemble. Let's say many commercial architecture may not need non-planar things, so then a clamp would be sufficient. Yeah, if that is okay.
Okay. Yeah, thank you very much. Maybe another question about the manual intervention. You mentioned that there are still some manual steps. What do you think in the future? Would it be possible to automate the whole process with robots, or we still need some people in the process?
Thank you. I think I looked at only, let's say, the technical part of the entire story about automation in architecture and specifically for timber structure. There are many parts that I did not look at. For example, I think one of the main barrier is socioeconomic factors, whether this is worth the effort at all. So if we only zoom into the technical part, I believe it is totally possible. Whether it will still make sense for the other bigger picture, I am not sure. But from a technical perspective, you can also have robots that automatically load material to the system. You can, by using that probabilistic model, we can design the correction mechanism that can accommodate the rest of the misalignment problems. However, as I say, no process is really 100% reliable. there will always be a need for monitoring systems, either automatic or manual. And then there will always be need for people to fix things that are found to be not okay. You know, once the monitoring system says something went wrong, probably human intelligence would be more flexible in dealing with these problems than trying to anticipate the 0.01% of what could go wrong. And that, I think that's my take on it. Yeah.
So a last question, more a technical question. Usually when we use robots for assembly tasks, we use force control. And is this something you investigated?
Yeah. So the robotic arms that are downstairs, they are normally operated in position control mode, and that is how I thought I would construct everything, because then it's, you know, absolute positional accuracy. However, what I found that during the clamping of the joints, I actually need to give some flexibility to both the stationary side, which is the partially assembled structure, and the robotic arm. Since the partially assembled structure can sometimes be quite big and it's, you know, half constructed, I cannot ensure that it's always that side being able to deform until things align. So I used impedance control for that final clamping moment. For this clamping moment, no, this is position control. For the tightening of the screws, it is the last moment when I need to tighten the screw to the torque requirement. That part is torque control. Yeah. So otherwise, to pull the two joints together is position control. Yeah.
You think that it's for the clamping system, so it's not worthwhile to use impedance control in the future?
This I actually don't know well enough. Let's say the approach that I have taken with this one is it's a brute force device. It's designed to be more force than it's needed, so it will not lose its synchronicity with the robot side. If we enter the area of having torque control or impedance control, then it's hard to synchronize also with the robots that are not, you know, under the same umbrella. But this part I do not know. Yeah.
Okay. Thank you very much.
Can I continue? Yeah. Okay. So Victor, let me start by congratulate for the super concise and exciting and Silke called it dense. It's super dense presentation. I was wondering how you were going to do this, because with a PhD, written PhD of about 400 pages that are also, you know, pretty, you know, full of details and stories and sub-stories, to you know, boil it down to something that you can easily understand and make sense, and that is a nice story. It's demanding and very well done. I also was thinking when you were presenting a big handicap of the written work is that you cannot use movies that often explain things extremely clearly, you know, in a very, very short. You immediately understand what the problem is, and if you describe this, then it's text and diagrams and tables and things, so it's not easy. Maybe you should also rethink the way this should be, and I think your PhD is probably from the point of view of, let's say, the detail, level of detail that you offer to the reader and to the other researcher, probably the most comprehensive one. So there you almost feel that you could, you know, start where you left off. Yeah, and this is, it's I think for this kind of research an extremely important quality to consider as part of the research result. Now, after this, you know, appreciation of the work, I would like to. I mean, I have tons of questions, but the one that to which I always come back, talking to you and now seeing the work. So you're really on once you start by analyzing. And you really look at the processes. I think the whole first year was about looking at how these things are done on the building site and all the situation. And at a certain point, there is this spark, this invention that solves everything, but also creates a big problem because it's not done yet. You know, saying, okay, let's distribute. I think that at first sight seems very simple and banal, but it's not. You know, you need all this work to get there and say, okay, we have the RFL, it's for robots, but this cannot be the solution. We need to distribute these things, and there it's where also your work becomes extremely pragmatic, in a good sense of the term. So you observe that humans distribute things. So you have different tools, and you have different people on a building site, and if this would not be orchestrated, it just wouldn't work. It would be chaos, and stuff would jam, and so on and so forth, and then you start to translate this into hardware and software, of course, to control this. And there it's where it becomes extremely exciting, but also hard. And there again is where I think your specific knowledge that you presented at the very beginning was crucial to be able to solve it. If you wouldn't be able to bridge the domain of mechanical engineering as an architect, you know, this would be all wishful thinking. You wouldn't be, you know, have done these prototypes, and they wouldn't have been applied to 4 experiments and so on and so forth. And this makes it extremely graspable. So again, congratulations for that. Now, let me translate to the question or to the open point let's say that your work generates. For me, it's the question, what do the human do? And this is the fundamental question. You also addressed it. I think very honestly, you said that you did not look at it technically. So you distinguish between technical feasibility and then its meaning in a broader context. And there, I think sometimes you're a bit shy. I think I agree that this is a good way to keep things clean and apart. But as a designer, you are in here, you know, in all those things, and sometimes you show yourself, you know, you define yourself the operator, and this is something ambiguous between just being another tool, you being another distributed tool, you being the agent that fixes the problem, you being the process engineer, you being the inventor, you being the designer, but not of all structures. You know, some you let students design, others collaborate, or one you design by yourself. So you by not naming it, by keeping it open, you know, you also create a certain expectation, you know. And this is, you know, connects to a question Agati already raised. How do you imagine these things, you know, beyond what you have analyzed? What do you imagine the role of the architect, or of the designer, or of a future craft person would be in such a process? Because I think where you know, in this very nice last step that was not planned, where you look at this probabilistic model, there you said a very nice thing. There you said, at a certain point you realized that it's not about automating it. It's about finding out how likely, you know, this will run smooth. What in reverse for me means to what extent you have to be there to intervene. And then you can decide if a thing makes sense or not, depending on a context. Yeah. So what is this future perspective?
I think the imagination is actually quite exciting. There are many new roles that I discovered, which, as you say, is all just me, to bridge that gap of people who don't exist yet. Let's say the people who design joints are currently timber engineers who don't necessarily know what are the best features for a robot to assemble them. For example, currently they're a process engineer, but obviously they don't look at how timber is assembled. So there's a very new and interesting gap in understanding who is going to design the robotic process, who is going to design the joints that can go into them, who's going to design these tools. And I don't know how to define them. It's like how to define what I do. And I couldn't find a word because I think that role, that stereotypical persona, doesn't exist at the moment. And I guess that's kind of what, you know, people coming out from this building is good at, which is a little bit of everything that can glue everything together. We can talk to engineers that can solve the hard problems, but we kind of, I don't know. The operator, if you specifically talk about the operator side or the craft person side, I think there's a lot of room in the journey from, let's say, trying to automate this to getting there. And this will be a very long journey. And that is the point where the operator or the person who monitors the system can give meaningful feedback to the designers of the system, whether be it's the tool designer or the people who design the structure. Maybe there is a certain thing that about even the architecture, the design, when you design the structure, it's just not stable and the stability calculation is not right. You need someone that comes with that sort of feedback. So I don't know, it's a very messy thing. There are many roles that has to be filled. There is a written list in the thing at the end, you know, at around the 400th page. Then I kind of list out what have to be done. But yes, I think it will. This, or let's say, what we do in this building, have been challenging us to think about what are these new roles in society in the future if this is reality. If this is reality.
Okay, thanks. I maybe give it over to you. Then we can
Sure.
make a second round.
Thanks a lot. I also like very much your very comprehensive presentation and PhD, the number of pages to be acknowledged again, but also the detailed nature with how, in a way, I could say you open source your thoughts, the failures, the findings, etc. I think it's very valuable as a way of sharing research. For future steps to be taken. Also, I would like to commend you on the kind of collaborations and the efforts that you've taken across multiple disciplines and working, you know, with, in a way, people from computer science, mechanical engineering, structural design, etc. So I think that speaks a lot about this kind of integrative nature of the work that you had been tackling, with all the consequences. Let me start maybe from just a small, very technical question, because I would be interested, because you were talking about this probabilistic method, and you said that you kind of would dream about some kind of statistical prediction, and my question was, what kind of data would you need in order to make that prediction?
Yes, so there are a few data, super exciting. This is depending on what parameters you want to feed into the system. Let's say that's a very short diagram of what kind of deviation can exist in the system. Let's say, for example, robotic accuracy. This is something that you can both characterize, measure, and for, let's say, the flexibility of the gantry, you can do statistical measurements that can characterize that into a sort of statistical distribution of how wrong it can be. It can even be related to the configuration. For example, if you're constantly holding something like this, the robot is more likely to be like, so you can characterize these things. You can collect data, and practically speaking, the RFL, you would mount a sensor. The IGPS would be the perfect candidate for and then measure in different orientation, different payload, and ideally, because there's so many degrees of freedom, you would want to machine learn it for sure. For the correction mechanism, that is the design, for example, of the camera, how wide angle lens, what's the size of the markers, that will determine the range of how it works, and that is two of the parameters that feeds into the equation. Scaffolding, so that is structural analysis, classical ones, but it also requires analysis that is going into this non-deterministic nature. For example, if you have a column, it can either be left or right. It's kind of undeterministic because it's
in simulation.
That one will have to be done in simulation, and there are things called statistical probabilistic structural simulation that give. Lucky that Philip left. Just left. And then that is just the amount of chamfer, yeah.
Okay, good, thanks. I was just curious because, I mean, this would be then part of a methodology, how to apply it. Okay, how do you get to the data in order to use, let's say, your methodology?
All the terms in this formula are statistical distributions.
Sure, okay, thanks. Now, maybe a bit more, I have kind of two vectors, maybe two more questions to ask there. One goes towards applicability. Maybe could you tell a bit about the limitations but also prospects? Maybe I can offer you two ways here. One is, for example, a question of speed, you know, and practicability of what you have here. Maybe some reflections on that, and maybe to challenge you a bit or tease out where this could go. If you now were to do a startup on this, what would you do? What would you put out in the market? What do you think, or how far would you need to develop this further to propose something, and what would you propose?
I see myself as an academic.
No way out.
I can imagine. Let's talk about speed. The speed of the system is very, very slow. I'm not going to hide this away. It's written in the thesis. It's extremely slow. Being able to give you an idea, clamping together one joint or screwing one joint takes around 5 to 6 minutes. You didn't hear it wrong. Minutes to just assemble one joint. With a strike of a hammer, a carpenter can do this in no time. But at the same time, the point of the thesis is also not, you know, trying to chase speed, because I'm sure, you know, this is my DIY stuff. You know, if an engineer actually put time into making it faster, I'm pretty sure it can be very fast. And therefore, I retreat back to the academic discussion. I think a startup requires, in my experience with startup, you need a very good business model, and you need it to work financially. And that is not something I know how to do, and speed is definitely one of the major challenge. Another thing is about startup is you need to see what's the financial gain by doing this instead of the current status quo. And I also don't know how to evaluate this. I'm pretty sure it's slower and you need a robotic setup to do this, which is not going to be cheap. One thing that I did look into is who else on earth have an RFL-looking robot doing construction, and that is Japan. There are 3 to 4 different Japanese companies that have what they call automatic building machines, which are the size of a building. And one of the analysis that people talk about is the only reason why they can do it is because the way how Japanese corporations are arranged in a way that they are very big corporations that can spend money. For other countries, smaller companies, you just cannot spend that much of investment up front to do these type of research. So I don't know, startup would be really tricky.
How many years do you think it will take until this becomes a reality?
How many people are you going to give me?
Let's say 25.
Oh, that is going to be quick. No, but I think, I don't know, I don't have business. I mean,
no,
you can definitely automate this with 25 people and, have it super automatic, but then whether it's going to make clients and stuff,
I guess, no, my question was also a bit in the direction of, I mean, you developed a lot of software, you have kind of planning systems, you develop mechanical components, and then you have a timber prefabrication system in a way. I mean, of course, you could also go in parts of what you had been developed and saying, okay, maybe that part is ready, other parts take some more time.
Yeah. I think there are many smaller areas in my research that are extractable and reusable in many other contexts. Yeah, I'll just leave it as that.
I'm a bit surprised that you do not, of course you can refuse the question saying you're an academic, but normally if you have, this is the ambitious plan, this is a long-term plan, this is a, very hard thing to, needs time, but in an idea you always have some low-hanging fruits, so things that could be combined with others, already, give some advantages, objective advantages. And I can imagine here that not these clamps directly, but the logic behind them, so having power tools that are moved manually, that can talk to each other, and can, in a concert, include the humans that are already on the job, could in certain specific situation. I'm not sure. This should, of course, would need proper analysis and so on. But I'm not so sure if it's just 0 or 1. First you have to develop this full automatic vision before being able to make some money from the perspective of startup, of course, but from the perspective of research, also to give back some, advantages to the industry, you know, out of the research. But this doesn't have to be your job, of course. There, I'm fully with you. This is, and this is why it's so important that these things is properly documented, gets disseminated, and is available for whoever is, you know, wanting to push it one step further.
Thank you for answering that for me.
I see a lot of potential. No, it would be a pity.
Yes, I think this concept of distributed robotic tools can be very promising for other fields. So I'm pretty convinced that we could use this concept for other fields. So large-scale robotic systems. Because it goes in the direction of mobile robotics, but maybe we could combine this type of tools with mobile systems as well.
Now that you mentioned mobile robotics, maybe I will let me undersell this a little bit. So the idea of distributed tools is not new. People have been doing mobile robots, you know, things that walks around and you know, clean your floor and stuff like that. And there's but their focus is mainly on autonomy in terms of locomotion. And the main idea is that they need to be able to navigate around through obstacles, and they have their own propulsion system, which makes them very complex. And you know, half of the effort is to just make it be able to move around and not bump into things and break things. So this approach is just tapping onto that and say, okay, don't let the tool deal with its own locomotion. Just do one thing and do it really well, is to clamp the joint. And let someone who is with something which is the robotic arm that is really good at dealing with locomotion spatially, particularly in our case 9 joints, so you have a lot of freedoms to deal with the locomotion. So I think that is the, let's say, key selling point of this.
Thank you very much. We have also a few minutes for questions from the audience. Yeah, I just see the first hand coming up. May I ask a first question? I know your project is about timber assembly, but I was wondering, have you also thought about disassembling, and could you like also rewind the whole process?
Yes,
put it in.
That would be very nice. I thought about this because obviously clamp you cannot unclamp. You know, once you cannot unclamp. Screw you can unscrew. And a lot of timber structure is dealt with dry joints, so you can totally disassemble the whole thing. Obviously, you need to keep very good documentation of the digital model that you have, so that later on you can, you know, rewind the whole thing. This is extremely exciting because if you think about like modular construction, that looks like you know, a container box. You can ship it back to the factory, and then the factory can do all the disassembly as long as you still have the model intact, and more or less the joints are dry joints. I mean, certain things you can drill out, like a Revit you can drill out, but that would be quite cool.
Maybe an idea for a business plan also. But I would like to hand over.
Thank you, Victor, for this very nice presentations. I'm very impressed. My question is all about like how can we push this actually into the more like solid or more like market way. I think first with like prefabrication, right? Most of your stuff is doing prefabrication. And I think the key point is that you can make it, if you can make it faster than human. If you cannot make it faster than human, people will a little bit concerned. So what do you think is the first thing you will do for the next to make it faster? And my second question is, of course, we cannot prefabricate a super large house in our factory and ship. The transportation will be impossible. How do you think your tools can be used on site? And which kind of robots we need to design for, like, to use your tools in on site?
Like 2 chapters. Fast first. You know, it's like 2 chapters. Fast. First, let me say that I don't agree that fast is the only attractiveness in this process. For example, we have a lot of 3D printers down there. It takes, I don't know how long to print one object. But the only thing that you care is that you press a button and you don't have to look at it anymore, and you come back after a certain time. This is called lights out production in automation in factories. And that is cool too. You don't need to be necessarily competing with humans in this. If you have a very repetitive product, you can do full automation, and that alone would already be attractive from an industrial process perspective. If you really have to make it fast, the tools are the first one to improve. Most of the components here are off-the-shelf components. The motors are from my home country, and they could be better. So those can be faster. The third question is outside, on-site. Yeah, dangerous territory. Let's say the idea of distributed tools and the fact that they are quite modular. I mean, you can imagine this works in RFL, but you can also imagine that a crane on site can dock to this and put this where it's needed. I mean, it's quite heavy, but the tricky part is accuracy for on-site robots, whether they can keep up with something like this. Robots are, you know, even though they're made of metal, they are still quite flexible. And when things are big, they are even more flexible. And that is quite a mismatch for the architecture type of assembly that we need to deal with. No matter you're doing, you know, concrete or steel or wood, the generally expected accuracy is very, very high compared to such a big robot. So that is a question of whether robots will catch up in terms of better accuracy or better correction system, online corrections, or whether the joints that we can design with, let's say, for example, when you're building a bridge, you have joints that are way huge, you know, like tapered concrete surfaces that will guide itself into places. Maybe, but I think that would be the direction if we have to tackle the on-site challenge. It will be tricky. Yeah.
Are there some other questions?
Thank you, Victor. It's been an honor to join this journey. After all those sleepless nights, you know, after all those efforts, I watch your presentation, I still get goosebumps here.
That is Yi lent me his superpowers on motion.
Yeah, so my question is about, since you mentioned the Japanese efforts, we all know this, you know, this history of architectural robotics. It started in 1980 in Japan. You know, people start to develop those super specialized robots, like, you know, clean the surface. Basically, one robot specific mechanical design for a specific task. We all know it's kind of sort of died down in the 2000s. It's coming back. And then we have the second goal in architectural robotics, quoted by Martin Beckhold in Harvard. And like architects start to use those industrial arms as ways to, you know, connect their design to fabrication. And I see like your approach is kind of moving some way circle back to that early idea. We start to have this specialized tool for, like your tool is about timber assembly, right? But like if we going down this route, as you said, like one tool can do certain things really well. And we have a, you know, more general purpose robot that can walk around the site and manipulate those tools. How do you think, maybe can you give us a reflection, maybe like how this time those specialized efforts be different compared to the last one? Like technology advances, and what's different here? What can you give us like a vision or kind of where the construction robotics is going?
I will try. Help me out a little bit. Dr. Huang, I'm an academic. Yes, I don't know the answer. It is a very big question where robotics is heading to. I don't know the answer. It is construction is a very delicate business, not just about technology, but also about what makes sense financially, and probably 90% about what developers care, and then what happens on site is because financial reasons, not because, you know, whether technology can or cannot. In fact, if there is a financial goal, usually the technology will happen. The situation in Japan, as I have read, is quite unique, and that is also related to the social construct and how the economy is arranged, and that enables certain exploration. I don't know if other countries can do something similar, or even institutions or private can really do this. But one thing for sure is that investing in smaller tools like these ones are cheap, very cheap. This is 2,000-ish, not counting my labor. And And it's a very easy entry point for small research endeavors to start, such as my project, which is on a short budget. But since we already have the RFL, which is already there, people can tap into it. Let's say someone who wants to create a startup can tag along and say, hey, I want to test this sort of mobile thing. You know, maybe it assembles not timber, but you know, steel, I don't know, concrete or clean glass, I don't know. Can we try to do the spatial work with the RFL robot, and I bring this thing to test? That is a much easier entry, which I guess goes with the startup thing that you talked about. And I think financially that is most likely to work than to say, let's come up with a new company that would do a big machine that's bigger than a building and put these things inside. That is, I think, very difficult to start.
If I can just ask one small question.
No.
I was
Yes.
I was in ICRA, the biggest robotics conference, the annual conference for robotics last week in London. And I've seen this sharp comparison between two camps. The first camp is kind of mechanical engineering and computer science, very excited, full of excitement and energy. They try to get robots to replicate the human's dexterity. Either industrial arm trying to open up a lid, tear a little tape, that kind of thing. You see a lot of fancy algorithms over there. Or you try to get a robot just to walk without falling down. This is one camp. And on the last day of the conference, there's a workshop about construction robotics. I was sitting in the room, and I just feel like there's an air of despair. And like people just, everything's unstructured, nothing really works, and you know the economic aspect is not really clear. And there's essentially just two types of robotic processes involved in the workshop. The first one is excavation, autonomous excavation, and our friends, Ryan and RSL is pushing that effort. And the other is scanning, the scanning of the construction site and trying to bridge the gap between the BIM model. And I just get really confused about, as a person, trying to bridge these two fields together. How can we recruit more students to get into construction robotics? Because we all know it's a very important field, and we have a lot of technical problems. And do you see, like, you know, these type of distributed tools may be the key, maybe the entry point? Like, for example, like we have a lot of domain knowledge in construction. We can encode them into those tools. And then, you know, more general purpose robots can come here and try to work with these tools. Maybe that's just one way to get these two things go together.
I think that would make it easier entry for both research projects and also for startup endeavors. The bad atmosphere that you experience, I don't know how to fix. I think that is, you know, if you started with a story, I will answer with a story. A few weeks ago, went to the Venice Biennale, and there was not much architecture in the Architecture Biennale. And it was mostly statements that are apologetic in nature. And I don't know why, but I think it's a bigger wind that we are under.
No, I think for construction robots, it's about the things are not structured enough.
So do you have a final last question, short question? No. Okay. So thanks. If somebody else has a short final question. Okay, yeah.
Thank you very much for this great presentation. Victor, I wanted to talk about time. You said that this is very slow, watching a joint, and I'm just, when you said that, I thought, how long would it take for Japanese carpenters to actually build this thing? I'm not sure. I mean, do you know? Have you ever? Yeah.
So,
hey.
Yeah, no. The HyperHut demonstrator, we disassembled it after the experiments, and we brought it to Lausanne. And Mike and how many people helped? 3, 4. I know you were in a disassembly team. Was even faster. The assembly team was 3 people. In 2 hours, it's done. 2 hours with a battery drill, easy.
Is that because you already knew what you were doing?
That's also true, yes.
And if we brought
That is true.
drawings to carpenters, and they wanted to do that in the craft.
I think carpenters are very smart people. They look at it, they know what to do. It is not that tricky.
So just compared to your time, do you think it would be 25% of the entire time to build that? Humans would do it in 25%?
No. I built that in 2 weeks. There, 2 weeks, yeah, compared to 3 hours of 3 people. Yeah. Thank you, yes, but still, there is a big difference between weeks and hours. Yeah, but I think we can make it faster if you're interested. we can, it's possible. Yeah.
So, Victor, thank you very much. Thanks to the board for the question and to the audience. We are going behind closed doors now for some minutes or for quarter hour, and then we see back. Yeah. Thanks a lot.